We'd like to welcome our newest addition to the group, who's moved from Moravia to Bohemia, Mauro Mantegazza, of Charles University, who will speak about jet functors in non-commutative geometry.
Thank you for the opportunity of giving this talk, especially since it's almost exactly 1 year after the first time me and my collaborators, Keegan Flood and Harry Quinter, came here to present the problem for the first time. So today I hope to give an updated version of the current state of the art. Okay, so the aim of our research is to describe and use jet functors in the setting of non-commutative geometry. And I will start by explaining every single word of the title. Let's start from non-commutative geometry. What do you mean by this? So, the starting point of non-commutative geometry, as it often happens in geometry, is the translation between geometry and algebra. So the idea is that we have a geometric object and we want to study it through the tools of algebra. So we consider functions over this geometric object that have a certain regularity and that somehow capture the geometric properties of our geometric object. So if the algebraic representation is good enough, then we can retrieve completely the original object. And that allows us to identify the algebraic object with the geometric object. So the good thing about the algebraic object is that it can often be naturally generalized. So in this case, what we do in non-commutative geometry is we remove the axiom of commutativity. So instead of considering a regular our algebra of functions, sorry, I think so. Yep. Yep. Maybe I'll keep it up. Does it work? Yep. Hello. Hello. 1, 2, 3. Maybe you have to select. Okay. I go with hello. Does it work? No. Hello. Okay. Maybe yes. Okay. How do I remove this? I don't. Okay, well, I'll leave it there. Okay. So as I was saying, we remove the axiom of commutativity. So instead of taking a commutative algebra of the regular functions, we take a generic associative unit algebra over a commutative ring K. Okay. So there are several approaches to non-commutative geometry, but the one that we are using, in a sense, restricts well to the classical case. So the idea is that if we have something that already has a classical meaning and we want to generalize it, we want this general to be compatible with the classical one. Okay. Now let's see. It doesn't work anymore. Okay. Okay. I will try not to not. Okay. Yes. Okay. So now we have. I wrote this table as a sort of translation tool. So we have the classical geometric object, the equivalent algebraic one, the non-commutative generalization, and what these generalizations represent. So let's start from the R or C. So usually our geometry, especially in differential geometry, will have a field of scalars, R or C, and in algebra, of course, that corresponds to a field. And in our generalization, we will consider a generic commutative unitary ring. Now, a manifold, which algebraically is represented by smooth functions, at least in differential geometry, smooth functions over the manifold R. This is generalized by a generic unital associative K algebra. Now, a vector bundle will be algebraically associated to space of sections, which has the structure of a infinity M left module in general, infinity M module. And by the Sturm theorem, we know exactly what these modules are. So these modules are equivalent. The category of infinity modules that represent sections are finitely generated projective left modules. So this is what Sturm theorem tells us. And finally, whenever we have a bundle map from two bundles V and F, this corresponds algebraically to a C infinity M linear map, and the generalization is, of course, a left A linear map. Okay, so this is the generic setting. I can't. I can. Okay. Yeah, this is easy. Okay. Okay, so let's see some useful categories. So we have the category of finally generated projective modules, which is embedded in the category of projective modules, which is embedding in the category of flat modules, which leads in A module. Okay, first of all, modules will be denoted, the category of modules will be denoted by putting the algebra to the left or to the right, depending on where the algebra is. Now let's go to the properties. So flatness, by flatness, I mean the algebraic flatness, which means that the corresponding functor given by tensoring is exact. So this functor is normally just right exact, but we ask also it to be left exact. And the reason why I recalled it here is that I don't want it to be confused with the geometric notion of flatness, which means we have a connection and the curvature is zero, because that notion is particularly restrictive, whereas this notion is pretty natural to us, since geometrically it more or less corresponds to the fact of having local triviality, which in particular every bundle has. In fact, we can see that finally generated projective modules are in particular flat modules. Okay, then by projectivity, I just mean that it's a module such that for every epimorphism, for every surjective morphism and every map from P to the codomain, we have a lifting, a compatible lifting to the domain. So this is the notion of projectivity. And of course, finitely generated means finitely generated in the sense of modules. So there is a finite set of generators. Okay. Okay, so far we talked about the topology of this object. Now we are going to give the differential structure to this object. So what we need is a sort of generalization of the de Rham complex. So what we have is an associative graded algebra, which we denote by omega bullet D and wedge the operation, such that the 0th degree is the algebra itself. And then we have a map which is k-linear, and it behaves as the differential. So it increases the grade of the algebra. It squares to 0. It satisfies this graded Leibniz property, and it is generated by the algebra and the differential of the algebra. So we call this particular axiom surjectivity axiom because we'll see that it will induce some useful properties. So we can see, if we're familiar with the de Rham complex, we see that these are exactly the properties of the de Rham complex, with the exception that we don't ask the graded commutativity. And that's because otherwise in degree 0, that would force commutativity on A, which we want to avoid. Okay. So this, of course, is a commutative example, but we will now see a non-commutative example, which is somehow the cleanest one, although one of the poorest in terms of geometry. That's called the universal exterior algebra. How does it work? As the first grade, we take the kernel of the multiplication map from A tensor A to A. And as differential, we take the mapping that maps an element A into 1 tensor A minus A tensor 1. So we can see that it goes exactly where we want it to go because the product is 0. And now we describe the higher terms by tensoring the one grade with itself n times. this corresponds also to the so-called tensor algebra, which will come back. And then, yes, we set the wedge product to be the tensor product. So it's a sort of, that's why as an algebra, it is exactly the tensor algebra. And of course, the D extends to the whole algebra by the Leibniz property and linearity, alinearity and Leibniz property. Okay, so as I said, the universal exterior algebra is geometrically very poor, but luckily it gives us this universal property that tells us that whenever we have another exterior algebra, omega bullet B on A, then there is a unique epimorphism from the universal algebra to the exterior algebra, and it's unique up to it's the unique one that is compatible with the exterior algebra structure. So the grading, the differential, and the wedging. Okay, if we want to see the map explicitly, the element sum of AI BI is mapped to the AI goes as coefficient of the forms, and the BI goes as so the DBI will be the form element. Okay. And now let's move to differential geometry. So I will now describe the object that we want to generalize, which is the jet bundles. So let's start with a vector bundle over a manifold, and let's consider a point on the manifold. Then, since every bundle, vector bundle, is locally trivial, we can find the so-called trivialization that is a map of this form. So we have a first component that maps that we call X, that this represents the coordinates on the base, and we have a component phi which represents the coordinates on the fiber. Okay, this map is useful because it allows us for every section to interpret this section as a map from Rn to Rm, for example, so a real map essentially. So what we do is we take a section, generic section, we pre-compose it with the coordinates, so that we live now in R dimension of the manifold. And then we compose it with the vertical component. And this goes in general in R rank of E. But if we take every single component, this goes just in R. So these are real functions defined on an open subset of R dimension of N. So how do we use this trivialization? For every couple of sections, we consider the corresponding real functions, and we define the relation where two sections are equivalent if and only if the two corresponding real functions coincide up to order n in their Taylor polynomial. So it turns out that, first of all, this relation is independent of the trivialization chosen. So it's a property that really depends on the sections themselves. And second of all, it's an equivalence relation. So what we get is we consider the classes of this equivalence relation, which we call nth order contact at the point P. And this is the jet. So we can see a jet of a function as a sort of nth order approximation of that function at the point. Okay, so it turns out that jets, if we call Jn of E the set of all jets on a bundle E, of sections of a bundle E, turns out that it comes equipped with a structure of vector bundle. In particular, we take the approximation, which we denoted this way, nth order approximation at P goes to the point P. This gives, as I said, a structure of vector bundle. And yeah, as I said before, we have to interpret this as the bundle of nth order approximation. So keep this in mind. Okay, so why are they useful? So first of all, as we saw, they are reminiscent of a notion of Taylor approximation. And since this notion is independent on the trivialization chosen, it's an intrinsic notion. So jets are used to define an equivalent of Taylor approximation without charts or polynomials. Second reason why they're useful is because they help to give a definition, an intrinsic definition of differential operators, and we'll see this part at the end of the talk. And lastly, they're useful for the theory of differential equation. In fact, we can use them to define an intrinsic notion of differential equation, and we can develop through jets a theory to understand when these are solvable or not. Okay, a few properties. Notice that J0V is E itself. This because the zeroth order approximation of a function is the value of the function itself. So, yeah, given a section, the section will be mapped to its value, and that realizes the isomorphism. Then, more generally, if we are in a K-jet and we are on an n-dimensional manifold, we take a chart x1, xn, and we can see that the fiber of the jet bundle is given by polynomials with order at most k, with variables x1, xn, so the entries of the net, tensor EP, which means these are polynomials, kth order polynomials in the coordinates with value in E. Okay, and here we can again see why Taylor is related to jets. Okay, so jet bundles come equipped with a couple of maps. We have the so-called n-jet prolongation, which is an R-linear map, and it's important that it's R-linear and not infinity n linear. Where for all n we have it maps a section of E into its nth order approximation. So this is the map that maps sections into their approximation. And then we have the jet projection, which essentially forgets the information at the higher degree. So we have n higher than n, and we forget the information of all the higher degree up to n. Okay, this is what we have. In particular, we have that J0 is the identity as well as phi from n to itself, just formality. And notice that this gives the isomorphism at the top. Okay. Okay. Okay, so this construction is functorial. In fact, if we have a map of vector bundles, we have a natural way of mapping a jet into the jet of the image, which is that. Okay, and yeah. And with this functorial structure, it turns out that the maps we defined before, so prolongations and projections, are natural transformations. Okay, this natural transformation in particular satisfy these two rules, which will be important later. And what they mean is that we can forget the information all at once, or we can forget it in two steps. Doesn't matter. And what this means is that if we take a section, we see its nth order approximation, and then we forget the last part. What we get is the approximation to the lower order of the same section. This is what it means. So this, in a sense, is the compatibility. This makes sense to the J, and this makes sense to the phi. Okay. Okay. So as I mentioned at the beginning, our aim is to find a notion of jet bundle, so a generalization of the notion of jet bundle and jet functors to the setting of noncommutative geometry. And the property we use to do so is the following. So every jet bundle fits in this short x-dot sequence, where we have as the map phi is the projection to the degree -1, and the kernel of this projection is the symmetric tensors of order n. And here, once again, we can see why Taylor is important, because we are forgetting the highest term, and what we are getting as a kernel is exactly homogeneous polynomials of maximum degree, which is exactly what we get when we forget the information from polynomials. So in a sense, we can see that this short exact sequence encodes the whole structure of jet. So we really need this short exact sequence to work, and we can use it to produce our jet. Okay, so how do we do that? Sorry. Sn is are the symmetric tensor of order n in general. So it's a bundle of symmetric tensors of order n. Its sections are, yeah, they're basically polynomials in a sense with on the C infinity n function, but you can see them like that.
And is it, sorry, maybe I'm just being slow, no, but is it, why is this killed?
Sorry?
Why is this killed? As in it's So you say this is an exact sequence, so then S to the n is killed by pi n n minus 1. Is
no, I didn't get the point. Why is it? Okay.
is it in the kernel of this map?
Okay, well, it all depends on how you interpret symmetric forms into jets. But the idea is when you have so an nth order approximation, it happens pointwise in a sense. No, because it's pretty complicated. It depends a lot of how you put it.
So it's not so obvious in the end.
The SNs are jets where the value of the jet is 0, and the nth order approximation is the symmetric form. But then you get that every value of the jet is 0 at every order that is not the top one. So it's some sort of degenerate case where you have no substance, and the only thing is what matters here, and it doesn't matter here, because the moment you kill the top part, then you're left with the lower part, and the lower part has no information given by this guy. At the moment, I can't explain it better than this. So, yeah. Okay, so given the bundle short exact sequence, we consider the short exact sequence obtained by taking the global sections. And we know by Serre-Swan theorem that this map is an equivalence of categories. So this is again a short exact sequence. And now we are in the position to generalize, because now we have a module. Okay, so what do we want now? We want a functor of that generalize the notion of symmetric form. We want a functor that generalize the notion of jet, and we want them to fit in this short exact sequence. So we want inclusions of Sn into Jn, projection to the last component, and we want a family of prolongation, which must be k-linear, because as I said before, it's important that these are r-linear in the differential geometry case, and now r becomes k, so this must be k-linear. And they must be such that the two compatibility relations hold, as I said before. So this is our setting. So when we have this, we are satisfied. Up to some point, I will get back to it. Okay, so how do we use this information? Let's start with the quantum symmetric form. Okay, in differential geometry, when we want to take a differential form valued in a vector bundle, what we do at the level of section is we take the tensor product over C infinity of n of forms, differential forms, tensored with the global sections of it. So this is what happens. So it is natural to generalize this notion to the non-commutative setting by taking as a form functor the tensor functor by the exterior algebra and with each grading going in the appropriate grading. Okay, once we have that, we can give a definition of symmetric form. So in degree 0 and 1, we want these to coincide with the normal notion of form. And that's inspired by the classical case, and it makes sense. For n greater than 1, what we do is we see it as the kernel of this composition. And now we see what this composition means. But first of all, we notice that being a kernel of this composition, it's a submodule of this, which means Sn can be seen as living inside of omega 1. So one forms in Sn-1 symmetric form. Okay. So what we do to build this map is we take Sn-1 and we embed it into one forms in Sn-2, which exists by inductive hypothesis. Then we apply omega 1, which just means that the first component is not touched. And now we apply the wedge in the first two components. So asking the kernel of the wedge, we are basically saying that the wedge vanishes in that component, and that's what gives the symmetry. And we call it quantum symmetry because, of course, it doesn't in general correspond to the standard symmetry. So we don't have commutativity, but we have a symmetry induced by the exterior algebra.
Your calculus generated in degree 2 in sense as a quotient of a tensor algebra, your ideal is of degree 2, or it could be some higher order guys.
I am so my wedge goes in degree 2. That's sure. Or you mean the
I mean, we have a higher order forms. For example, for usual classical differential calculus, you take a ideal and you take an ideal of degree 2 in tensor algebra, generate. Well, you take a generate relations of degree 2 and you generate. Are you assuming here's the same, or your relations could be high order?
But actually, could be also higher order. I think I can put to 0 everything that goes beyond 2 in a sense. I think I can still do that. We are not assuming any maximality of the algebra. It's a generic case. Yeah, no, I was confused by the generated by.
Yeah, I mean,
generated as the forms, but
no.
The ideal doesn't matter. We can take like you can even die after 2. We don't care.
So it could happen. Could it happen that some of the symmetric forms will be also exterior because we have some high order relations?
This will pop up again, a bit hidden, but it's there in the Spencer cohomology. So if you consider a particularly pathological calculus where everything goes to 0 after the degree 2, I think you will have some troubles in getting vanished of the Spencer cohomology. So in a sense, we'll see.
There's a question in the chat, a few. So the first one is, why only to omega 2 and not higher omega n, from Edwin?
We'll see it's equivalent. It's enough to take omega 2. In the next page, it's right here. Okay.
There was another question about composition.
More
yeah, but it seems that Henrik is after answering this. Yeah.
So we can see that if we have reasonable assumptions on the exterior algebra, in particular omega 1 and omega 2 right flat as right modules, then Sn is equivalent to these other three formulations. In particular, we have this second one, which is important to us because what it means is that Sn on nice calculi is given by the intersection of the kernel of the wedge in each single position. So that's exactly what we wanted in a sense. So we want symmetry induced by the vanishing of the wedge, which is what happens classically, and it's what we wanted to model. So this would be a good notion of quantum symmetric form. Okay. Now that we have the quantum symmetric forms, we can build the Spencer cohomology. We define it as follows. So we embed SH into the corresponding one form on SH minus one, and then we apply the wedge. And now you can see that omega k is showing. And so this composition essentially is we forget the symmetric structure on the first component of the symmetric part, and we wedge it by the wedge. So we increase the antisymmetric part, and we decrease the symmetric part. Okay, given this map, we get a complex. This turns out to be a complex, and it does so because essentially if I apply it twice, this will have to be followed by something like this, but we know that the symmetric part is exactly where the wedge vanishes, so that's why the composition is revealed. Okay, so we get this complex, which is called the Spencer delta complex, and the corresponding cohomology is the so-called Spencer cohomology, and we'll see it will turn out to be important later. Okay, so finally we are able to define the jet bundles. And we start with the simplest possible case. So we consider the one-jet bundle over the universal exterior algebra, where E coincides with the trivial bundle. So E is equal to A, and geometrically corresponds to the trivial bundle, one-dimensional trivial bundle. Okay. What do we do? So we know that S1 coincides by definition with omega 1 of U, which again, by definition, coincides with the kernel of the multiplication. So we have a natural map of this form. As I said earlier, the zero jet coincides with the module itself. So this is a good candidate for the zero jet. This is F1 of U, and therefore we can define this central element as the universal one jet on A. Notice in particular that it's the free one-dimensional A bimodule. Okay, now as projection, of course, we take the product, as I said before, and as prolongation, we take the map that maps an element A into one tensor A. And we can see that it splits the sequence as we want. And it's also the only, it's the only one that splits the sequence that is also right alinear. And we won't write a linearity for it to be compatible with sections whenever I substitute A with B. This is just, we'll see it later in specific cases. Okay. So now we have the short exact sequence, the universal short exact sequence, and what we want to find is a generic one jet exact sequence. Okay. Yes.
Quick question. What is the symmetric, guys, in the universal sense?
I will compute it.
Okay, great. Thanks.
At the end of the result, I will compute it. Also the Spencer component. Okay, so we have this, now that we have these two maps, what we can do is we take the epimorphism that exists by the universal property of the universal exterior algebra, and we take the identity for A. This commutes, of course, because the horizontal compositions are zero, so it really commutes. And yeah, and recall that PD is, so this whole diagram happens in A bimodules. This is important. But this happens in A by modules, but if we forget the right module structure, this is also a diagram in left A modules where A is a projective element. And whenever we have a projective module, we have a unique extension. So there is also a unique map between J1U of A and J1D of A. This map for now is only left A linear, but we'll use it for the construction. Okay, so this is a diagram in left A modules. We take now the kernels and the co-kernel, and we see that everything is 0 except for the kernel of the projection from the universal to the exterior algebra, which we call ND, and these two mysterious objects, kernel and co-kernel of the central extension. Okay, so now we can apply the snake lemma. Apply the snake lemma, and it turns out that the snake long exact sequence must be exact. So co-kernel is forced to be 0. So P hat D is forced to be surjective. And the kernel of P hat D is forced to be isomorphic to ND. But now we see that we don't only have a map from, like we can basically identify the kernel of P hat D with ND, because we can see ND inside of omega 1 of U and omega U inside of J1 of U of A. So we do that.
So how is P hat sub D defined again? This I missed.
Defined by the uniqueness of the. So whenever you have two short exact sequences which represent extensions, and you have a map like external maps, if the object is projective, you have a unique map. But more like without going through properties or anything. If A is projective, the sequence splits. So as a left A module, in this case, this will be represented by direct sum. So these two are direct sum, and we can see them as matrices. Basically, we can choose this mapping so that it's compatible with the identity here and with the inclusion there. So it's, but we'll see now it will become less important because this is just how we find the form of the one jet. We will find an explicit description and then it will be clear what we have. Yeah, A tensor A by N. Yeah, exactly. Okay, so as I said, we identify ND with the kernel of P hat D. And since the P hat D is an epimorphism, we can identify J1D of A. I mean, J1D of A is forced to be A tensor A over ND. But now PD is A bilinear, which means ND is an A bimodule, which also means that this quotient is an A bimodule and the projection to the quotient is A bilinear. So we started from something left A linear, but now we actually got something bilinear. Regarding the prolongation, we have the universal prolongation, and if we compose it with the P hat D, of course, we have the prolongation in the general case. Okay, so what we do is we define J1D of A as the tensor, as the quotient of the universal A tensor A over ND. We take as a projection the product again, but this time applied to the class. And there's prolongation, this map, so one tensor A in the class. And now we can see that the P hat D is precisely the mapping that maps A tensor B into its class. So that's why it's very important. Okay. All right. Yes. Okay. So for so far we only worked on the trivial bundle, and to obtain a generic bundle, what we do is we tensor on the right by the generic left A module, and since the map J1D splits the sequence in right A module because it's right A linear, The operation happens on the right. It turns out that the sequence we get is still exact. And so this is our jet. That sequence. Okay, so what we can do now is keep applying the one jet n times to itself. So this functor, which will turn out to be the tensor power of the one jet. The tensor functor corresponding to the tensor power. But this is not the higher jet. These are not the higher jet. In fact, they contain, in a sense, too much information to be the one jet. But they're still important because we can see the actual jet inside them. So that's why we'll use them. Just to give definitions, we have the non-holonomic jet prolongation, which is the composition of the prolongation, and therefore it corresponds to tensoring by one on the left several times, n times, to be precise. And we have many jet projection which correspond to taking the product in every single position n. Okay, so this is the non-holonomic jet functors, but I will not go into depth with them. I will just use them to find the two-jet functor. So the two-jet functor must satisfy this property. So we want this property to be satisfied. But what we have so far is if we apply the one-jet exact sequence to J1D of E as a module, we get this. We get the one-jet exact sequence of J1D. And we notice that we have the one jet here, just as above. We have the non-holonomic two jet below. And here we have this object. Now, we can, it makes sense to assume that, as in the classical case, the first sequence embeds in the second. Well, embed is a strong term, but we want the sequence to enter, to be interpreted in the second. So we consider this situation like this. Okay. Now, if we assume omega-1 to be flat, we know that the tensor product is exact, and in particular, it preserves injectivity. And this map was injective as well as this one, which means this becomes injective, and by the snake lemma, this also becomes injective. Okay, so we can see the two jet inside the non-holonomic two jet in this case, this particular case. So what makes sense to do is to consider what necessarily has to be inside, which is S2 of D, must live inside J2 of D, and the prolongation of elements of E. How do the prolongations work? We want, as in the classical case, we want them to be compatible with the non-holonomic one. So it's again tensoring by one and then tensor A. And it turns out that if you consider what I mentioned before, so if you consider the sub-bimodule generated by jet prolongation and symmetric forms inside of J2 of D, it turns out that this submodule does satisfy the two-jet short exact sequence. So this is a good candidate for the two-jet, but that's not enough. In fact, we want to see it as kernel of a certain linear map. And we managed to find this map, and this map is we denote it with this Icelandic letter as tilde of E. The image of this map is this special place with which is defined as a tensor functor, and as a right A module it behaves as a direct sum, whereas as a left A module it has this weird action that mixes the terms. So one forms, part of the one forms become two forms. Okay, but it doesn't matter. What matters is that we have made a linear map whose kernel is precisely the two-jet. And this is the form of the map. How do we use it? We use it in the spirit of the definition of quantum symmetric differential operator. So there we wanted to define Sn as the kernel of wedge in every position. Here we want to define jet as the kernel of F tilde in each position. So in a sense, F tilde is what gives the relation that make a generic non-holonomic jet a holonomic jet, and we want it to happen in every single position. This is the spirit. And in fact, this is the definition. So we see it as a kernel of F applied to the first two. So we have the Jn-1, which embeds in J1, Jn-2, and then the first two components get mapped by F. And the kernel is what we define.
So the bimodule structure that you have, that in the classical case, it's still a strange bimodule structure.
You mean on
the previous slide, yeah. Because
the bimodule, okay, so for now you have a left bimodule structure, but if E is a bimodule, then you also have a left bimodule structure. You have on the right the split action.
Yeah.
And on the left you have this weird action, but it's still a bimodule map.
but this is a non-commutative phenomenon then. I mean, if you're considering E as a bimodule, then yes.
Yeah, in fact, we have two actions,
Mhm,
this object, and we can see that the right action, when we have the right action, that corresponds to the splitting, which appears in the short exact sequence. So in a sense, already in the classical case, we have two different actions. The problem is that commutativity makes it so that they look like there are two different actions of the same thing, but the non-commutative description sort of shows that the left one is the bundle action and the right one is the splitting action. So it's this other weird splitting. So in a sense, it looks like the real environment for jet is the non-commutative geometry. Surprise. Surprise.
Good answer to the question, huh?
Well, classically, you have this action, weird left action too, to which geometric structure it corresponds.
The left action?
Yeah, on the previous slide, this star.
The star is actually the bundle action, so component-wise, because the elements get a bit mixed up. But the left action corresponds to the bundle set. So you take a function and multiply at every point by the value of the function at that point. So the point is action. And the right one is the action given by the splitting. It's we call it the APIA action, although I don't know who's the inventor of that. You can find it on the end page of APIA.
It's just because of this weird structure of semi-direct product that after isomorphism, it will split into action onto direct sum, just multiplication, right?
As a bimodule, on the right, it will split. Yes. Yes. Although it will not split as a bimodule, but as a right module.
I'm more curious about the left guy.
It can split as both, but sorry, as both independently. So it splits as a left module, it splits as a right module, but it doesn't split as a bimodule in general.
Okay, am I right also then? We have this right splitting that is written, and then we have this action by star. And if I will split with respect to right splitting, the left action will be something like multiplying.
It mixes the two.
Okay, so
yeah, it mixes the component.
Holonomic mean?
Holonomic just means that you have it's basically that you have jets. It's I don't know how to explain it better, but let's say when you do one jet over a module, you're taking this one first order approximation. When you take two jets, what you want is second order approximation. But what you get if you apply the one jet twice is you get first order approximation of first order approximation. And that's not the same thing. Holonomicity means that you're relating the differentials of differentials to square differentials. You know, broadly speaking, very broadly speaking. in a sense, derivatives in the direction of derivatives make sense as if they were two derivatives. I can go to detail, but like philosophically speaking, this is the idea. So holonomic means that there is a relation between the various levels to obtain a notion of higher order proximity. Okay. Yes, we have a definition of higher jet as kernel of that map. And if we compose the inclusion of the various inclusion of each jet into its J1 of Jn-1, we get the map from holonomic jet to non-holonomic jet. But in general, it's not injective unless omega-1 B is right A flat, which again is a reasonable assumption, but it also shows that I mean, it's in general, in very wild cases, it can not happen that it's injected, but that doesn't scare us because that also happened in synthetic differential geometry. So if we're in a setting that's weird enough, weird things can happen. Okay. So now we can define the missing elements. So we have the jet projection, which is defined by taking the n jet into the one jet of the n-1 jet and taking the product on the first part and then going to the Jn-1. We define a more general projection by composing these elementary projections. And we define the inclusion of Sn into Jn by the commutativity of this diagram. I will not enter into details of how this is built, but it turns out to exist because of the kernel universal property. Okay. So now some results. So first of all, our jet under reasonable assumptions do satisfy the short jet exact sequence. Now the first assumption is flatness, and as I said, we don't have to be scared of it, but the second assumption is still a bit scary. That is until we think of the meaning of Spencer cohomology, which should more or less correspond to the solvability of differential equations. And the bundle E is itself the solution of the differential equation 0 = 0, so the trivial equation. So it makes sense that this equation is integrable. So in a sense, by turning plates around, a good notion of bundle will have to be such that the Spencer cohomology on it vanishes. This is the claim. Okay, so if the Spencer cohomology vanishes, then we have the short exact sequence. This is the first result. Second result, it does generalize the classical case. So if instead of A, we take C infinity of M, and instead of omega D, we take the Terán complex. And then if we take a vector bundle E, the E jet, so the sections of the jet bundle will correspond to our notion of jet module. So it's compatible with the classical case. And same with projection, prolongation, and so on. And now, finally, we compute the information for the universal exterior algebra. So recall omega n is the tensor power of omega 1 with itself. Omega 1 is defined as the kernel of the product. And the wedge is just the tensor over the algebra. Okay. Can compute the various degrees. The degrees 0 and 1 are given by definition. And as we said, the 0th degree of E is E itself. And the first degree of S1 is omega 1 of E. Now for the second case, the second grade, we have to, well, it's exactly the kernel of the wedge, this by definition in degree 1. But now we see that S1 of U is omega 1 of U, and omega 2 of U is by definition also omega 1 of U tensor omega 1 of U.
And the wedge, which is the tensor over A, starts from a tensor over A, so it corresponds exactly to the identity, and the kernel of the identity is 0, which means that S2 of U is 0. And this implies that for any n greater than 2, also Sn is 0 because it's included by inductive hypothesis into something that is 0. So as long as one grade is 0, every higher grade must be 0 because it's inside omega 1 of 0. Okay, so as a recap, we have S0, which is E, S1, which is omega 1, and everything else is 0. So this is the situation. We can build the Spencer delta complex in generic K and H, and we see that everything is 0 except for the terms in S1 and S0. S0 here disappears because it's the identity, and here S1 is just omega 1. The circle is just the tensor product, so and as well as this. So this is omega 1 tensor K plus 1, as well as this. So it's the tensor algebra in both cases, and the wedge again corresponds to the equality. So the Spencer delta complex is trivially exact. So the Spencer cohomology benefit everywhere. And now we describe the jets. So it turns out that without any assumption, so remember that the theorem before was asking for omega 1, 2, and 3 to be rightly flat. And for the Spencer cohomology to vanish. Now, we already know that the Spencer cohomology vanishes, but we don't know anything about the omega 1 of U, because since K is a generic ring and not a field, we don't know if omega 1 of U is right flat. But regardless, without that assumption, we still get this presentation of jets. And we get that they fit in the jet shortcut sequence. So the 0 jet is E, and the n jet is in general A tensor E. The nth prolongation is 1, applying the tensoring by 1 on the left. And the projection is just the product action. So A tensor E goes into E. Okay. Okay. And we'll use this structure to compute differential operators, which I'm now going to define. Okay. So classically, let's come back to classical differential geometry. What is a differential operator and why are they related to jets? Well, it turns out that we can define them intrinsically without mentioning partial derivatives of any or anything else like that, by this universal property. So whenever we have a map which is R-linear from sections of E to sections of F, we say that it is a differential operator of order most n if there exists a bundle map from the jet bundle to F such that it fits, it commutes in this diagram. Particularly if n is minimal, then we have we say that the differential operator is exactly of order n. Okay. Yes. So what we have now is, if we remember how jets were constructed, every point is of this form, and this is clearly the image by the jet prolongation, which means delta tilde is completely determined by delta. So given a delta, if delta tilde exists, it's unique. And that means that the functor of differential operators on E is representable with the representative object, the jet bundle itself. That's because by definition, so this map in a sense is surjective, because by definition, every map that is compositional A-linear with Jn is a differential operator, and it's injective because of the uniqueness of the idea. Yes. Sorry.
Which category do your Ham sets live in? It's enriched over sets, or it's?
Okay, so these are homomorphisms of vector bundles. And these, well, this is just the differential operators from me. It just for now will become something else. Yeah, if you want the map from here to here is the well, you take first the gamma, the total sections, and then you pre-compose with JM. Okay, so this is the situation at the differential geometry level. And now let's see how we generalize it. Okay, let's take two left-ray modules, E and F, and we say that a k-linear map delta from E to F is a linear differential operator of order at most n if there exists a module map, so a linear, from the n jet on E to F, such that it commutes in this diagram. And again, we say that it's minimal if we say that it's of order n if n is minimal. Okay. So let's see in particular, differential operators of order 0 are a linear map. That's because J0 is the identity map, as we saw before. And so the only way for delta to be listed is for it to be exactly a linear map. Okay. Yeah. So another example. So we remember that the universal one jet, and in general every jet, they're of this form, A tensori. And we see that for every k-linear map from E to F, there is a natural extension. So it turns out that the universal differential operators are just k-linear maps. And they're all either first order or zeroth order if they're also a linear. So this again underlines the fact that the universal exterior algebra doesn't really convey much geometric information, it's just purely algebraic. Okay, so it turns out that everything that we can reasonably extend, that we could think of, that we can reasonably extend to the non-commutative setting, turns out to be a differential operator. Particularly, we have connection that we will discuss in detail now. We have the differential, which is also a differential operator. We have partial derivatives, which are defined in a particular sense. They're also differential operators. And we can see that since the F tilde was a linear, we can recompose it with the jet prolongation to get a differential operator. So it turns out that jets are defined in a sense as a solution of a differential equation by the differential operator F. And that explains why we carried the tilde for so long until now. That's the final review. Okay, so now connection, let's see in detail. So there is an already known notion of connection in non-commutative geometry on a bundle, on an A module E with respect to a certain first order differential calculus. That is a k-linear map maps sections of E, well, sections, elements of E to one forms with values in E that satisfy the Leibniz property. This is the definition. We know it's not a linear because it satisfies the Leibniz property, but but it's k-linear, and we have a natural lift of this object, which we denote with u here, lambda tilde of u. And it turns out that it vanishes on the elements in ND, which I recall was the kernel of the natural map from omega 1 of u to omega 1d. Okay. In particular, there are elements of this form such that they belong to omega 1 of u, so the product of these two is 0. And when I apply PD of E is 0. So if we take a generic element of that form with the lift, we apply the definition of the universal lift and we get this object. And now we apply the Leibniz rule and we get that this is the product, which vanishes because these elements are in omega 1 of u. And this is precisely PD of E by definition. It used to be reversed, but it's actually equivalent to that because they live in omega 1. It doesn't matter. What matters is that this vanishes, and therefore the nabla tilde of u factors through the quotient of omega of the universal jet by nd of v, which was by definition the one jet of v. Okay, therefore it follows that nabla is a differential operator of order 1. And we see that it's not really important that nabla is a connection. Like what really matters is that it vanishes on objects of this form, and this provides a criterion in general for establishing when a k-linear map is also a differential operator of order 1.
Question from Edwin. It's, can you get back from a first order differential operator to a connection?
I'm not sure. I have to think about it, but so in general, no. I would say because zeroth order differential operators are also at most first order differential operators. So if I take something that happens to already be a zeroth order differential operator, I wouldn't be able to find a connection. But there might be a way by removing this zero part, but I don't know if there is a canonical. I don't think there is a canonical. I don't know. So in general, no, let's say that the connection might be closer to purely first order differential operator, and in that case, I'll have to think about how to go back. Okay. Another interesting property of connection is the fact that the lifting from the one jet to omega 1 of v is a splitting of the jet exact sequence, and turns out even more that connections are in one-to-one correspondence with the splitting of the one jet exact sequence, exactly as it happens classically. So this is another result that gets generalized perfectly to the non-commutative setting. Okay, final topic. Sorry, I'm already late. final topic is the category differential operators. As I mentioned before, we can interpret differential operators as the image of the precomposition by the jet prolongation. And since the jet prolongation is k-linear, differential operators are closed under k-linear combinations. Furthermore, if we have an nth order differential operator, this is also an nth order differential operator for n greater than m, and we obtain the corresponding lifting by just precomposing with the jet projection. And this sort of makes sense to the notion of at most of order at most n in the definition. And this provides a filtration of differential operators of at most certain order. Filtration that increases up until all possible differential operators, which are inside of k-linear maps, and the zeroth order differential operators that are a-linear maps. And in particular, the zeroth order differential operator from A to A is linear maps, which correspond exactly to the right multiplication by elements of A, and therefore it's an AO as an algebra. Then we have we can compose two differential operators, and by this procedure, it turns out that the composition of two differential operators is again a differential operator, particularly if delta 1 is of order n at most n and f is of order at most m, their composition will be of order at most n plus n. We see that the composition preserves the filtration, but not the exact grading. In fact, we can take from differential geometry the exterior covariant derivative, and we see that if we apply twice, we get the curve, the wedging by the curvature, which is a tensor, and therefore these are differential operators of order exactly 1, and this is a differential operator of order 0, because it's linear. So we see that, yeah, composition of first order differential operators might not be second order, and in fact, it's zero. Okay, so we have a composition, we have the identities because they are a linear map, so we have a category. is a category, and it's a category that is enriched over filtration. Okay. Yes. Not necessarily. Not necessarily. If it satisfies the Leibniz rule, it probably is a differential operator, but not necessarily. For instance, take again, well, you mean if it's purely a perturbed differential operator. Yeah, again, I don't think it necessarily does. Leibniz rule has, Leibniz rule implies differential operators, but not regular. Okay, I conclude with other results that we have. We have a way, we have constructed a way that we call S-terminal calculus, where we can take a set of k-linear maps between A modules and basically imposing them to be differential operators of order 1. And then we can provide the minimal calculus that has this property. So this is a tool to produce new exterior covariant, so a new exterior algebras. And we're probably able to do it with higher orders as well, but there are still things to be checked. Then we have certain conditions under which the non-commutative jet bundles are still representative object for differential operators. In general, it will have several lifts of the zero map, but if the situation is nice, then we again have the uniqueness of the lift and therefore representability. We have some more explicit criteria for k-linear maps to be differential operators in general order. We have a notion of symbol of a differential operator, which corresponds to the highest grade of the differential operator. But if you know what a symbol is, this is there to convince you, otherwise it's not important. And finally, we are finally able to define linear differential equations. We can do them either algebraically by setting a differential operator equal to a certain element of F. This would be a non-homogeneous differential operator, a non-homogeneous differential equation, whereas if there was a zero here, this would be differential equations. But if we want to proceed more in the style of Vinogrado by seeing the differential equations as submanifolds of jets, we can take as a definition of linear differential equation an A submodule of the jet bundle, and this would be a homogeneous differential equation, and to that will correspond a non-homogeneous one by taking a different. Okay, so that's it. Thank you for listening.
And before we start, there was a comment from Henrik to your question in the chat, and he's saying, just some info, unless you're deep into jet theory, holonomic jets should be considered synonymously to jets with no adjective.
Yeah, we still have to think about that. But we had some ideas, but now we don't know what's the result of it. So stay tuned for updates.
So any questions from the audience?
So yeah, you mentioned like synthetic differential geometry there before, right? And I don't know much about it, but I remember hearing something also about jets and jet bundles and things. Yeah.
And
So
that's different from this presentation.
Yeah.
Yeah, it's given in terms of this infinitesimal important element.
Okay.
Yeah, no, I don't remember the details, but it's
Somehow related, but not quite. Okay.
But yeah, They are a generalization of classical differential geometry that wants to be more algebraic in spirit. So they have these infinitesimals, and they build a natural notion of jet. And I think it was a completion of Whisker. I don't remember. But,
Is that a completion of
there was this object called Whisker, maybe, which was
whiskering? Okay.
a point with the two infinitesimals, and then now I don't remember if this was a connection or that. I don't remember the details, but
Right. Cool. Thanks.
there is its own theory, and we haven't drawn the parallel between the two.
Right.
Any more questions? I think, Bishan, you were.
Yeah, I mean, okay, first, just maybe a silly question. The word jet, is it supposed to be descriptive in some way? I mean, why are these things called jets?
Why are they called jets? Because they originally were born as jets of curves. And when you see the jets of a curve, is there a chalk here? So jets of curve meant as approximations of the curve. So if you have a point in a curve and you want to approximate up to a certain order, let's say second order, so they will have to have the same derivative, the same value at the point, same derivative at the point, so same tangent stuff, and also same curvature. So you will get something like this. Sort of. And this looks like a jet of water.
Okay, okay, yeah, no, fair enough, fair enough. Okay, and also, so were they designed to demonstrate existence of solutions to differential equations? Is this one? So can you do, like, relevant to the last point you had, very last point you had? So can you do a similar sort of thing in the non-commutative setting? Do they demonstrate existence? Okay.
We don't know yet, but it seems to be sort of generalizable. We should dig into the details, so everything might go bad in the end. But the elements are quite natural, so maybe we'll be able to still get some information. It would be nice if it worked. If we got an overdetermined PD theory of non-commutative geometry.
Yeah, no, that would be really cool. Thanks.
What you think could be a generalization of a solution?
Solution is so if we have a section, solution is an element E of E in this case, such that its prolongation fits entirely in this submodule. Or in this interpretation, it's just an element E such that delta of E is equal to F. This is a sort of algebraic notion of equation, which is, I call it etymological, because equation means to equate two things. And so if I want delta of E to be equal to F, then that's a solution. In the Vinogradov approach, it will be an E such that the prolongation of E, which is inside the n jet in general, if this is also inside the submodule, then it is a solution for this approach. So this is yeah. So the differential operator, in a sense, operates some conditions on the sections, and when they're equal to F, that's the solution. And we also have the same approach. So if we have the space of solutions of delta will be a K vector space, and the space of solution for the non-homogeneous case will be an affine K affine space. So that leads to
I have a few comments. The first comment is like, commend your spirit of hard work for doing these things over like non-flat calculi. But I mean, in any example you have, the thing shouldn't be not only flat, but projective. So I mean, any of the qualifications that you have here, I think you don't need to worry about it all. The next one is, as I usually say, of course, it seems almost certain that the examples coming from quantum groups, from quantum like manifolds will fit into this. Everything should work. Again, because you've been so careful doing everything generally, you just get all of your assumptions and more will be assumed for these examples. Yeah. Spencer cohomology, okay, that's probably the one that needs to be calculated, but that's, well. And then finally, just a comment again, I guess it would be, I mean, if you're talking about the principal symbol here, so then that would mean you're able to define elliptic and pseudo-elliptic operators.
In a sense, because the classical case can make sense of it by, in the classical sense, you have Rn, which is clean, like you can see the symbol can become a sort of polynomial, and you can see that it's positive and then elliptic, but here it becomes a bit more complicated. But still, yeah, given the symbol, you have you can have definitions, like a sort of compartmentalization of the differential curve, having the same symbols that share the same problem.
And like the question, given the C-star algebraic interests of half the audience, is like that if these things where you're dealing with were completable to C-star algebras, then it's possible that these would give you examples of Fredholm operators and hence K-homology classes. Yeah. Should be cool. Yeah. Okay, so are there any other questions, especially from online? Maybe. So if not, then I guess we'll